Introduction. Throughout history, the aim of astronomy has been to make sense of the universe. In the ancient world, astronomers puzzled over how and why the planets moved against the backdrop of the starry sky, the meaning of the mysterious apparition of comets, and the seeming remoteness of the sun and stars. Today, the emphasis has changed to new questions concerning how the universe began, what it is made of, and how it has changed. The way in which its constituents, such as galaxies, stars, and planets, fit into the larger picture and whether there is life beyond Earth are some of the questions humans still endeavor to answer. Understanding astronomy. The baffling cosmic questions of the day have always inspired big ideas to answer them. They have stimulated curious and creative minds for millennia, resulting in pioneering advances in philosophy, mathematics, technology, and observation techniques. Just when one fresh breakthrough seems to explain gravitational waves, another discovery throws up a new conundrum. For all we have learned about the universe's familiar constituents, as seen through telescopes and detectors of various kinds, one of our biggest discoveries is what we do not understand at all. More than 95% of the substance of the universe is in the form of dark matter and dark energy. The origins of astronomy. In many of the world's most populated areas today, many of us are barely aware of the night sky. We cannot see it because the blaze of artificial lighting overwhelms the faint and delicate light of the stars. Light pollution on this scale has exploded since the mid-20th century. In past times, the starry patterns of the sky, the phases of the moon, and the meanderings of the planets were a familiar part of daily experience and a perpetual source of wonder. Few people fail to be moved the first time they experience a clear sky on a truly dark night, in which the magnificent sweep of the Milky Way arches across the sky. Our ancestors were driven by a mixture of curiosity and awe in their search for order and meaning in the great vault of the sky above their heads. The mystery and grandeur of the heavens were explained by the spiritual and divine. At the same time, however, the orderliness and predictability of repetitive cycles had vital practical applications in marking the passage of time. Archaeology provides abundant evidence that, even in prehistoric times, astronomical phenomena were a cultural resource for societies around the world. Where there is no written record, we can only speculate as to the knowledge and beliefs early societies held. The oldest astronomical records to survive in written form come from Mesopotamia, the region that was between and around the valleys of the Tigris and Euphrates rivers, in present-day Iraq and neighboring countries. Clay tablets inscribed with astronomical information date back to about 1600 BCE. Some of the constellations we know today have come from Mesopotamian mythology going back even earlier, to before 2000 BCE. Philosophy is written in this grand book, the universe, which stands continually open to our gaze. Galileo Galilei. Astronomy and astrology. The Babylonians of Mesopotamia were greatly concerned with divination. To them, planets were manifestations of the gods. The mysterious comings and goings of the planets and unusual happenings in the sky were omens from the gods. The Babylonians interpreted them by relating them to past experience. To their way of thinking, detailed records over long periods were essential to establish connections between the celestial and the terrestrial, and the practice of interpreting horoscopes began in the 6th century BCE. Charts showed where the sun, moon, and planets appeared against the backdrop of the zodiac at some critical time, such as a person's birth. For some 2,000 years, there was little distinction between astrology, which used the relative positions of celestial bodies to track the course of human lives and history, and the astronomy on which it relied. The needs of astrology, rather than pure curiosity, justified observation of the heavens. From the mid-17th century onward, however, astronomy as a scientific activity diverged from traditional astrology. Today, astronomers reject astrology because it is unfounded in scientific evidence, but they have good reason to be grateful to the astrologers of the past for leaving an invaluable historical record. Time and tide. The systematic astronomical observations once used for astrology started to become increasingly important as a means of both timekeeping and navigation. Countries had highly practical reasons, civil, as well as military, to establish national observatories, as the world industrialized and international trade grew. For many centuries, only astronomers had the skills and equipment to preside over the world's timekeeping. This remained the case until the development of atomic clocks in the mid-20th century. Human society regulates itself around three natural astronomical clocks: Earth's rotation, detectable by the apparent daily march of the stars around the celestial sphere to give us the day, the time our planet takes to make a circuit around the Sun, otherwise known as a year, and the monthly cycle of the Moon's phases. The combined motion in space of Earth, the Sun, and the Moon also determines the timing and magnitudes of the oceanic tides, which are of crucial importance to coastal communities and seafarers. Astronomy played an equally important role in navigation, the stars acting as a framework of reference points visible from anywhere at sea. In 1675, British King Charles II commissioned an observatory, the Royal Observatory at Greenwich, near London. The instruction to its director, the first Astronomer Royal, John Flamsteed, was to apply himself diligently to making the observations needed for the perfecting of the art of navigation. Astronomy was largely discarded as the foundation of navigation in the 1970s, and replaced by artificial satellites, which created a global positioning system. You have to have the imagination to recognize a discovery when you make one. Clyde Tombaugh. The purpose of astronomy. The practical reasons for pursuing astronomy and space science may have changed, but they still exist. For example, astronomy is needed to assess the risks our planet faces from space. Nothing illustrated Earth's apparent fragility more powerfully than the iconic images, such as Earthrise and A Blue Marble, taken from space by Apollo astronauts in the 1960s. These images reminded us that Earth is a small planet adrift in space. As surface inhabitants, the protection afforded by the atmosphere and Earth's magnetic field may make us feel secure, but in reality we are at the mercy of a harsh space environment, blasted by energetic particles and radiation, and at risk of colliding with rocks. The more we know about that environment, the better equipped we are to deal with the potential threats it presents. What a wonderful and amazing scheme have we here of the magnificent vastness of the universe. Christian Huygens. A universal laboratory. There is another very important reason for doing astronomy. The universe is a vast laboratory in which to explore the fundamental nature of matter, and of time and space. The unimaginably grand scales of time, size, and distance, and the extremes of density, pressure, and temperature go far beyond the conditions we can readily simulate on Earth. It would be impossible to test the predicted properties of a black hole or watch what happens when a star explodes in an Earth-bound experiment. Astronomical observations have spectacularly confirmed the predictions of Albert Einstein's general theory of relativity. As Einstein himself pointed out, his theory explained apparent anomalies in Mercury's orbit, where Newton's theory of gravity failed. In 1919, Arthur Eddington took advantage of a total solar eclipse to observe how the paths of starlight deviated from a straight line when the light passed through the gravitational field of the Sun, just as relativity predicted. Then, in 1979, the first example of a gravitational lens was identified, when the image of a quasar was seen to be double due to the presence of a galaxy along the line of sight, again as relativity had predicted. The most recent triumphant justification of Einstein's theory came in 2015 with the first detection of gravitational waves, which are ripples in the fabric of spacetime, generated by the merging of two black holes. When to observe. One of the main methods scientists use to test ideas and search for new phenomena is to design experiments and carry them out in controlled laboratory conditions. For the most part, however, with the exception of the solar system, which is close enough for experiments to be carried out by robots, astronomers have to settle for a role as passive collectors of the radiation and elementary particles that happen to arrive on Earth. The key skill astronomers have mastered is that of making informed choices about what, how, and when to observe. For instance, it was through the gathering and analysis of telescopic data that the rotation of galaxies could be measured. This, in turn, quite unexpectedly led to the discovery that invisible, dark matter must exist. In this way, astronomy's contribution to fundamental physics has been immense. Astronomy's scope. Up to the 19th century, astronomers could only chart the positions and movements of heavenly bodies. This led the French philosopher Auguste Comte to state in 1842 that it would never be possible to determine the compositions of planets or stars. Then, some 2 decades later, new techniques for the spectrum analysis of light began to open up the possibility of investigating the physical nature of stars and planets. A new word was invented to distinguish this new field from traditional astronomy: astrophysics. Astrophysics became just one of many specialisms in the study of the universe in the 20th century. Astrochemistry and astrobiology are more recent branches. They join cosmology, the study of the origin and evolution of the universe as a whole, and celestial mechanics, which is the branch of astronomy concerned with the movement of bodies, especially in the solar system. The term planetary science encompasses every aspect of the study of planets, including Earth. Solar physics is another important discipline. Technology and innovation. With the spawning of so many branches of inquiry connected with everything in space, including Earth as a planet, the meaning of the word astronomy has evolved once again to become the collective name encompassing the whole of the study of the universe. However, one closely related subject does not come under astronomy: space science. This is the combination of technology and practical applications that blossomed with the establishment of the space age in the mid-20th century. If astronomy teaches anything, it teaches that man is but a detail in the evolution of the universe. Percival Lowell. Collaboration of science. Every space telescope and mission to explore the worlds of the solar system makes use of space science, so sometimes it is hard to separate it from astronomy. This is just one example of how developments in other fields, especially technology and mathematics, have been crucial in propelling astronomy forward. Astronomers were quick to take advantage of the invention of telescopes, photography, novel ways of detecting radiation, and digital computing and data handling, to mention but a few technological advances. Astronomy is the epitome of big science, a large-scale scientific collaboration. Understanding our place in the universe goes to the heart of our understanding of ourselves: the formation of Earth as a life-supporting planet, the creation of the chemical building blocks from which the solar system formed, and the origin of the universe as a whole. Astronomy is the means by which we tackle these big ideas. Introduction. The traditions on which modern astronomy is built began in ancient Greece and its colonies. In nearby Mesopotamia, although the Babylonians had become highly proficient at celestial forecasting using complicated arithmetic, their astronomy was rooted in mythology, and their preoccupation was with divining the future. To them, the heavens were the realm of the gods, outside the scope of rational investigation by humans. By contrast, the Greeks tried to explain what they observed happening in the sky. Thales of Miletus is regarded as the first in a line of philosophers who thought that immutable principles in nature could be revealed by logical reasoning. The theoretical ideas put forward 2 centuries later by Aristotle were to underpin the whole of astronomy until the 16th century. Aristotle's beliefs. Aristotle was a pupil of Plato, and both were influenced by the thinking of Pythagoras and his followers, who believed that the natural world was a cosmos as opposed to chaos. This meant that it is ordered in a rational way rather than incomprehensible. Aristotle stated that the heavenly realms are unchanging and perfect, unlike the world of human experience, but he promoted ideas that were consistent with common sense. Among other things, this meant Earth was stationary and at the center of the universe. Although it contained inconsistencies, his philosophy was adopted as the most acceptable overall framework of ideas for science and was later incorporated into Christian theology. Geometrical order. Mathematically, much of Greek astronomy was based on geometry, particularly motion in circles, which were considered to be the most perfect shapes. Elaborate geometrical schemes were created for predicting the positions of the planets, in which circular motions were combined. In 150 CE, the Greco-Egyptian astronomer Ptolemy, working in Alexandria, put together the ultimate compendium of Greek astronomy. However, by 500 CE, the Greek approach to astronomy had lost momentum. In effect, after Ptolemy, there were no significant new ideas in astronomy in this tradition for nearly 1,400 years. Independently, great cultures in China, India, and the Islamic world developed their own traditions through the centuries when astronomy in Europe made little progress. Chinese, Arab, and Japanese astronomers recorded the 1054 supernova in the constellation Taurus, which made the famous Crab Nebula. Although it was much brighter than Venus, there is no record of its appearance being noted in Europe. It is the duty of an astronomer to compose the history of the celestial motions through careful and expert study. Nicholas Copernicus. The spread of learning. Ultimately, Greek science returned to Europe via a roundabout route. From 740 CE, Baghdad became a great center of learning for the Islamic world. Ptolemy's great compendium was translated into Arabic, and became known as the Almagest, from its Arabic title. In the 12th century, many texts in Arabic were translated into Latin, so the legacy of the Greek philosophers, as well as the writings of the Islamic scholars, reached Western Europe. The invention of the printing press in the mid-15th century widened access to books. Nicholas Copernicus, who was born in 1473, collected books throughout his life, including the works of Ptolemy. To Copernicus, Ptolemy's geometrical constructions failed to do what the original Greek philosophers saw as their objective: describe nature by finding simple underlying principles. Copernicus intuitively understood that a sun-centered method could produce a much simpler system, but in the end his reluctance to abandon circular motion meant that real success eluded him. Nevertheless, his message that physical reality should underpin astronomical thinking arrived at a pivotal moment to set the scene for the telescopic revolution. In context. Key astronomer Aristotle. Before 465 BCE, Greek philosopher Empedocles thinks that there are four elements: earth, water, air, and fire. Aristotle contends that the stars and planets are made of a fifth element, ether. 387 BCE, Plato's student Eudoxus suggests that the planets are set in transparent rotating spheres. After 355 BCE, Greek thinker Heraclides claims that the sky is stationary and Earth spins. 12th century Italian Catholic priest Thomas Aquinas begins teaching Aristotle's theories. 1577 Tycho Brahe shows that the Great Comet is farther from Earth than the Moon. 1687 Isaac Newton explains force in his Philosophiae Naturalis Principia Mathematica. One of the most influential of all Western philosophers, Aristotle, from Macedonia in northern Greece, believed that the universe was governed by physical laws. He attempted to explain these through deduction, philosophy, and logic. Aristotle observed that the positions of the stars appeared to be fixed in relation to each other, and that their brightness never changed. The constellations always stayed the same, and spun daily around Earth. The Moon, Sun, and planets, too, appeared to move in unchanging orbits around Earth. Their motion, he believed, was circular and their speed constant. His observations of the shadow cast by Earth on the Moon's surface during a lunar eclipse convinced him that Earth was a sphere. His conclusion was that a spherical Earth remained stationary in space, never spinning or changing its position, while the cosmos spun eternally around it. Earth was an unmoving object at the center of the universe. Aristotle believed that Earth's atmosphere, too, was stationary. At the top of the atmosphere, friction occurred between the atmospheric gases and the rotating sky above. Episodic emanations of gases from volcanoes rose to the top of the atmosphere. Ignited by friction, these gases produced comets, and, if ignited quickly, they produced shooting stars. His reasoning remained widely accepted until the 16th century. Earth casts a circular shadow on the Moon during a lunar eclipse. This convinced Aristotle that Earth was a sphere. See also, consolidating knowledge, the Copernican model, the Tychonic model, gravitational theory. In context. Key astronomer Aristarchus. Before 430 BCE, Philolaus of Craton proposes that there is a huge fire at the center of the universe, around which the Sun, Moon, Earth, 5 planets, and stars revolve. 350 BCE, Aristotle states that Earth is at the center of the universe and everything else moves around it. After 150 CE, Ptolemy publishes his Almagest, describing an Earth-centered model of the universe. 1453, Nicholas Copernicus proposes a heliocentric universe. 1838 German astronomer Friedrich Bessel is the first to obtain an accurate measurement of the distance to a star, using a method known as parallax. An astronomer and mathematician from the Greek island of Samos, Aristarchus is the first person known to have proposed that the Sun, not Earth, is at the center of the universe, and that Earth revolves around the Sun. Aristarchus's thoughts on this matter are mentioned in a book by another Greek mathematician, Archimedes, who states in the Sand Reckoner that Aristarchus had formulated a hypothesis that the fixed stars and Sun remain unmoved and Earth revolves about the Sun. Unfashionable idea. Aristarchus persuaded at least one later astronomer, Seleucus of Seleucia, who lived in the 2nd century BCE, of the truth of his heliocentric view of the universe, but otherwise it seems his ideas did not gain wide acceptance. By the time of Ptolemy, in about 150 CE, the prevailing view was still a geocentric one, and this remained the case until the 15th century, when the heliocentric viewpoint was revived by Nicholas Copernicus. Aristarchus also believed that the stars were much farther away than had previously been imagined. He made estimates of the distances to the Sun and Moon, and their sizes relative to Earth. His estimates regarding the Moon were reasonably accurate, but he underestimated the distance to the Sun, mainly because of an inaccuracy in one of his measurements. Aristarchus was the real originator of the Copernican hypothesis. Sir Thomas Heath, mathematician and classical scholar. See also, the geocentric model consolidating knowledge, the Copernican model, stellar parallax. In context. Key astronomer Hipparchus. Before 280 BCE Greek astronomer Timacharis records that the star Spica is 8 degrees west of the fall equinox. After 4th century CE Chinese astronomer Yuxi notices and measures precession. 1543 Nicholas Copernicus explains precession as a motion of Earth's axis. 1687 Isaac Newton demonstrates precession to be a consequence of gravity. 1718 Edmund Halley discovers that, except for the relative motion between stars and reference points on the celestial sphere, stars have a gradual motion relative to each other. This is because they are moving in different directions and at different speeds. In about 130 BCE, the Greek astronomer and mathematician Hipparchus of Nicaea noticed that a star named Spica had moved 2 degrees east of a point on the celestial sphere, called the fall equinox point, compared to its position recorded 150 years earlier. Further research showed him that the positions of all stars had shifted. This shift became known as precession of the equinoxes. The celestial sphere is an imaginary sphere surrounding Earth, in which stars are found at specific points. Astronomers use exactly defined points and curves on the surface of this sphere as references for describing the positions of stars and other celestial objects. The sphere has north and south poles, and a celestial equator, which is a circle lying above Earth's equator. The ecliptic is another important circle on the sphere, which traces the apparent path of the Sun against the background of stars over the course of the year. The ecliptic intersects the celestial equator at 2 points, the spring and fall equinox points. These mark the positions on the celestial sphere that the Sun reaches on the equinoxes in March and September. The precession of the equinoxes refers to the gradual drift of these 2 points relative to star positions. Hipparchus put this precession down to a wobble in the movement of the celestial sphere, which he believed to be real and to rotate around Earth. It is now known that the wobble is actually in the orientation of Earth's spin axis, caused by the gravitational influence of the Sun and the Moon. Industrious, and a great lover of the truth. Ptolemy describing Hipparchus. See also, gravitational theory, Halley's comet. In context. Key astronomer Zhonghang. Before 140 BCE Hipparchus discovers how to predict eclipses. 1st century BCE Jing Fong advances the radiating influence theory, stating that the light of the Moon is the reflected light of the Sun. After 150 CE Ptolemy produces tables for calculating the positions of celestial bodies. 11th century Shinqua's dream pool essays explains that heavenly bodies are round like balls rather than flat. 1543 Nicholas Copernicus's On the Revolutions of the Celestial Spheres describes a heliocentric system. 1609 Johannes Kepler explains the movements of the planets as free-floating bodies, describing ellipses. The chief astrologer at the court of Chinese Emperor Ntie, Zhang was a skilled mathematician and a careful observer. He catalogued 2,500 brightly shining stars and estimated that there were a further 11,520 very small ones. Also a distinguished poet, Zhang expressed his astronomical ideas through simile and metaphor. In his treatise Ling Xian, or the spiritual constitution of the universe, he placed Earth at the center of the cosmos, stating that the sky is like a hen's egg, and is as round as a crossbow pellet, and Earth is the yolk of the egg, lying alone at the center. Shape but no light. Zhang concluded that the moon had no light of its own, but rather reflected the sun like water. In this, he embraced the theories of his compatriot Jing Fong who, a century earlier, had declared that the moon and the planets are they have shape but no light. Zhang saw that the side that faces the sun is fully lit, and the side that is away from it is dark. He also described a lunar eclipse, during which the sun's light cannot reach the moon because Earth is in the way. He recognized that the planets were similarly subject to eclipses. Zhang's work was developed further in the 11th century by another Chinese astronomer, Shen Kuo. Shen demonstrated that the waxing and waning of the moon proved that the moon and sun were spherical. The sun is like fire and the moon like water. The fire gives out light and the water reflects it. Zhang Hang. See also, the Copernican model elliptical orbits. In context. Key astronomer Ptolemy. Before 12th century BCE, the Babylonians organized the stars into constellations. 350 BCE, Aristotle asserts that the stars are fixed in place and Earth is stationary. 135 BCE, Hipparchus produces a catalogue of over 850 star positions and brightnesses. After 964 CE, Persian astronomer Al-Sufi updates Ptolemy's star catalogue. 1252, the Alphonsine tables are published in Toledo, Spain. These list the positions of the sun, moon, and planets based on Ptolemy's theories. 1543, Copernicus shows that it is far easier to predict the movement of the planets if the sun is placed at the center of the cosmos rather than Earth. In his greatest known work, the Almagest, the Greco-Egyptian astronomer Ptolemy produced a summary of all the astronomical knowledge of his time. Rather than producing radical new ideas of his own, Ptolemy mostly consolidated and built upon previous knowledge, particularly the works of the Greek astronomer Hipparchus, whose star catalogue formed the basis of most of the calculations in the Almagest. Ptolemy also detailed the mathematics required to calculate the future positions of the planets. His system would be used by generations of astrologers. Ptolemy's model of the solar system had a stationary Earth at its center, with the heavens spinning daily around it. His model required complicated additions to make it match the data and allow it to be used to calculate the positions of the planets. Nonetheless, it was largely unchallenged until Copernicus placed the sun at the center of the cosmos in the 16th century. Ptolemy produced a catalogue of 1,022 star positions and listed 48 constellations in the part of the celestial sphere known to the Greeks, everything that could be seen from a northern latitude of about 32 degrees. Ptolemy's constellations are still used today. Many of their names can be traced even further back to the ancient Babylonians, including Gemini, Cancer, Leo, Scorpio, and Taurus. The Babylonian constellations are named on a cuneiform tablet called the Mul-Apen, which dates back to the 7th century BCE, however, they are thought to have been compiled about 300 years earlier. The constellations devised by Ptolemy are used in this 17th century star map. The number of stars per constellation ranges from 2 to 42. Early quadrant. To improve his measurements, Ptolemy built a plinth. One of the earliest examples of a quadrant, his plinth was a huge rectangular block of stone, one of whose vertical sides accurately aligned in the north-south plane. A horizontal bar protruded from the top of the stone, and its shadow gave a precise indication of the height of the sun at noon. Ptolemy took daily measurements to obtain accurate estimates of the time of the solstices and equinoxes, which confirmed previous measurements showing that the seasons were different lengths. He believed that the orbit of the Sun around Earth was circular, but his calculations led him to the conclusion that Earth could not be at the exact center of that orbit. Ptolemy the astrologist. Like most thinkers of his day, Ptolemy believed that the movements of the heavenly bodies profoundly affected events on Earth. His book on astrology, Tetrabiblos, rivaled the Almagest in popularity over the following 1,000 years. Ptolemy had not only provided a means to calculate planetary positions, but he had also produced a comprehensive interpretation of the ways those movements affected humans. Ptolemy describes the design of his stone plinth in the Almagest. It was a quadrant, an instrument that measures angles between 0 degrees and 90 degrees. Claudius Ptolemy. Ptolemy was a polymath and produced works on a wide range of topics, including astronomy, astrology, geography, music, optics, and mathematics. Very little is known about him, but he probably spent all his life in Alexandria, the Egyptian seaport with a reputation for scholarship and a great library, where he was taught by the renowned mathematician Theon of Smyrna. Many of his prolific writings have survived. They were translated into Arabic and Latin, disseminating his ideas across the medieval world. Geography listed the locations of most of the places in the known world, and was carried by Christopher Columbus on his voyages of discovery in the 15th century. The Almagest remained in continual use in academia until about 1643, a century after Ptolemy's model of the universe had been challenged by Copernicus. Key works: c.150 CE Geography, c.150 CE Almagest, c.150 CE Tetrabiblos. See also: the geocentric model, shifting stars, the Copernican model, the Tychonic model, elliptical orbits. In context. Key astronomer Aryabhata. Before 350 BCE, Heraclides Ponticus, a pupil of Plato, proposes that Earth rotates once a day on its axis. The idea does not become widespread because it contradicts Aristotle, who is considered more authoritative. 4th century BCE, Aristotle states that Earth is stationary in space. After 950 CE, Iranian astronomer Al-Sijzi supports the idea that Earth rotates. 1543, Nicholas Copernicus states that Earth rotates as part of his heliocentric model of the universe. 1851, the first demonstration of Léon Foucault's pendulum in Paris provides the final scientific proof that Earth is rotating. From the 4th century BCE to the 16th century CE, the prevailing view throughout the Western world was that Earth is stationary and located at the center of the universe. Suggestions that Earth might be rotating were dismissed on the grounds that this would cause objects on Earth's surface to fly off into space. In India, however, an astronomer named Aryabhata was convinced that the movement of stars across the night sky was due not to the stars revolving in a distant sphere around Earth, but to Earth itself rotating. An illusory movement. According to Aryabhata, the stars were stationary and their apparent movement toward the west was an illusion. His notion of a spinning Earth was not widely accepted until the mid-17th century, a century after Nicholas Copernicus had endorsed the idea. Aryabhata's achievements were considerable. His book Aryabhatiya was the most important work of astronomy in the 6th century. Essentially a compendium of the fundamentals of astronomy and relevant mathematics, it greatly influenced Arabic astronomy. Among other achievements, Aryabhata calculated the length of the sidereal day to a high degree of accuracy, and devised original and accurate ways of compiling astronomical tables. He was the father of the Indian cyclic astronomy that determines more accurately the true positions and distances of the planets. Helene Sellin, historian of astronomy. See also: the geocentric model, the Copernican model, the Tychonic model, elliptical orbits. In context. Key astronomer Abd al-Rahman al-Sufi. Before 400 BCE, Democritus suggests that the Milky Way is made of a dense mass of stars. 150 CE, Ptolemy records several nebulae in the Almagest. After 1610, Galileo sees stars in the Milky Way using a telescope, confirming Democritus's theory. 1845, Lord Rosse makes the first clear observation of a spiral nebula, now known as the Whirlpool Galaxy. 1917 Vesto Slipher discovers that spiral nebulae are rotating independently of the Milky Way. 1929 Edwin Hubble shows that many spiral nebulae are far beyond the Milky Way and are galaxies themselves. Abd al-Rahman al-Sufi, once better known in the West as Asafai, was a Persian astronomer who made the first record of what are now understood to be galaxies. To al-Sufi, these fuzzy, nebulous objects looked like clouds in the night sky. Al-Sufi made most of his observations in Isfahan and Shiraz, in what is now central Iran, but he also consulted Arab merchants who traveled to the south and east, and who saw more of the sky. His work centered on translating Ptolemy's Almagest into Arabic. In the process, al-Sufi tried to merge the Hellenistic constellations with their Arab counterparts, most of which were totally different. The fruit of this labor was Kitab Suwar al-Kawakib, or the Book of Fixed Stars, published in 964 CE. The work contained an illustration of a little cloud, which is now known to be the Andromeda Galaxy. This object was probably known to earlier Persian astronomers, but al-Sufi's mention is the earliest record. Similarly, the Book of Fixed Stars includes the White Ox, another cloudy object. This is now named the Large Magellanic Cloud and is a small galaxy that orbits the Milky Way. Al-Sufi would not have been able to observe this object himself, but would have received reports of it from astronomers in Yemen and sailors who crossed the Arabian Sea. The Large Magellanic Cloud, seen here above the ESO's Paranal Observatory in Chile, can be easily observed with the naked eye from the southern hemisphere. See also, Consolidating Knowledge Examining Nebulae Spiral Galaxies Beyond the Milky Way. In context. Key astronomer Guizhou. Before 100 BC Emperor Wu of the Han Dynasty establishes the Chinese calendar based on a solar year. 46 BCE Julius Caesar reforms the Roman calendar using a year length of 365 days and 6 hours, and adds a leap day every 4 years. After 1437 the Timurid astronomer Ulugh Beg measures the solar year as 365 days, 5 hours, 49 minutes, and 15 seconds using a 164-foot gnomon. 1582 Pope Gregory adopts the Gregorian calendar as a reform of the ancient Julian calendar by using a 365.25-day year, the same year as Guizhou calendar. The traditional Chinese calendar is a complex blend of lunar and solar cycles, with 12 or 13 lunar months matched up to the solar-derived seasons. It had first been formalized in the 1st century BCE during the Han Dynasty, and used a solar year of 365.25 days. China's calculations were ahead of the West's. 50 years later, this same period was used by Julius Caesar to create the Roman Empire's Julian system. By the time the Mongol leader Kublai Khan conquered most of China in 1276, a variant of the original calendar, the Daming calendar, was in use, but was centuries old and in need of correction. The Khan decided to impose his authority with a new, more accurate calendar, which became known as the Shaoxi calendar. The task of creating it was entrusted to Guizhou, the Khan's brilliant Chinese chief astronomer. A trained engineer, Guizhou invented a water-powered version of an armillary sphere, which is an instrument used to model the positions of celestial bodies. Measuring the year. Guizhou's job was to measure the length of the solar year, and to this end he set up an observatory in Kanbalik, a new imperial capital that would one day become known as Beijing. The observatory may have been the largest anywhere in the world at the time. Working with mathematician Wang Chun, Guo began a series of observations tracking the motion of the sun throughout the year. The two men traveled widely, setting up another 26 observatories across China. In 1279, the pair announced that there were 530,593 days to a month, and that the true solar year was 365.2524 days long. This is just 26 seconds longer than the current accepted measurement. Again, China was ahead of the West. The same figure was not independently measured and adopted for the universal Gregorian calendar in Europe until 300 years later. Enduring calendar. A great technological innovator, Guo invented several new observational devices and made enhancements to the Persian equipment that had begun to arrive in China under Kublai Khan's rule. Most importantly, he built a giant gnomon to a height of 44 feet, which was 5 times taller than the previous Persian design and featured a horizontal crossbar marked with measurements. This allowed Gua to measure the angle of the sun with far greater accuracy. The Shaoxi calendar was widely regarded as the most accurate calendar in the world at the time. As a testament to its success, it continued to be used for 363 years, making it the longest-serving official calendar in Chinese history. China officially adopted the Gregorian calendar in 1912, but the traditional calendar, today known as the rural or former calendar, still plays a role in Chinese culture, determining the most propitious dates to hold weddings, family celebrations, and public holidays. Gua Shoujing. Gua Shoujing was born into a poor family in the north of China, in the years when the Mongols were consolidating their control over the region. A child prodigy who had built a highly advanced water clock by the age of 14, Gua was taught mathematics, astronomy, and hydraulics by his grandfather. He became an engineer, working for the emperor's chief architect Liu Bingzhong. In the late 1250s, Kublai Khan took the throne and chose the region around the town of Dadu near the Yellow River to build the new capital of Khanbaliq, now known as Beijing. Gua was tasked with building a canal to bring spring water from the mountains to the new city. In the 1290s, Gua, by now the Khan's chief science and engineering advisor, connected Khanbaliq to the ancient Grand Canal system that linked to the Yangtze and other major rivers. In addition to continuing his astronomical work, Gua oversaw similar irrigation and canal projects across China, and his theoretical and technological innovations continued to influence Chinese society for centuries after his death. See also, shifting stars improved instruments Zhu Chongji. In context. Key astronomer Ulugh Beg. Before. c.130 BCE Hipparchus publishes a star catalogue giving the positions of more than 850 stars. 150 CE Ptolemy publishes a star catalogue in the Almagest, which builds on the work of Hipparchus and is seen as the definitive guide to astronomy for more than a millennium. 964 CE Abd al-Rahman al-Sufi adds the first references to galaxies in his star catalogue. After 1543 Nicholas Copernicus places the Sun as the center of the universe, not Earth. 1577 Tycho Brahe's star catalogue records a nova, showing that the fixed stars are not eternal and do change. For more than 1,000 years, Ptolemy's Almagest was the world's standard authority on star positions. Translated into Arabic, Ptolemy's work was also influential in the Islamic world up until the 15th century, when the Mongol ruler Ulugh Beg showed that a lot of the Almagest's data were wrong. A grandson of the Mongol conqueror Timur, Ulugh Beg was just 16 years old when he became ruler of the family's ancestral seat at Samarkand in 1409. Determined to turn the city into a respected place of learning, Ulugh Beg invited scholars of many disciplines from far and wide to study at his new madrasa, an educational institution. Ulugh Beg's own interest was in astronomy, and it may have been his discovery of serious errors in the star positions of the Almagest that inspired him to order the building of a gigantic observatory, the largest in the world at the time. Located on a hill to the north of the city, it took 5 years to construct and was completed in 1429. It was there, with his team of astronomers and mathematicians, that he set about compiling a new star catalogue. Giant instruments. Ptolemy's catalogue had largely been derived from the work of Hipparchus, and many of its star positions were not based on fresh observations. To measure accurately, Ulugh Beg built the observatory on an immense scale. Its most impressive instrument was the so-called Fakhri sextant. In fact, more like a quadrant, it is estimated to have had a radius of more than 130 feet and would have been 3 stories high. The instrument was kept underground to protect it from earthquakes and rested in a curved trench along the north-south meridian. As the sun and the moon passed overhead, their light focused into the dark trench, and their positions could be measured to within a few hundredths of a degree, as could the positions of the stars. In 1437, Zijai Sultani was published. Of the 1,022 stars included in the Almagest, Ulugh Beg corrected the positions of 922. Zijai Sultani also contained new measurements for the solar year, planetary motion, and the axial tilt of Earth. These data became very important, enabling the prediction of eclipses, the time of sunrise and sunset, and the altitude of celestial bodies, which were needed to navigate. Ulugh Beg's work remained the definitive star catalogue until Tycho Brahe's, nearly 200 years later. The religions disperse, kingdoms fall apart, but works of science remain for all ages. Ulugh Beg. All that remains of the Fakhri sextant is a 6½ ft wide trench gouged in a hillside. The observatory was destroyed after Ulugh Beg's death in 1449 and not discovered until 1908. Ulugh Beg. The name Ulugh Beg means great leader. The Sultan, astronomer's birth name was Mirza Muhammad Taragay bin Shahrukh. He was born on the move, as Timur's army traveled through Persia. His grandfather's death in 1405 brought the army to a halt in western China. The ensuing fight for control of his lands was eventually won by Ulugh Beg's father, Shahrukh. In 1409, Ulugh Beg was sent to Samarkand as his father's regent, and by 1411, as he turned 18, his rule over the city was extended to include the surrounding province. Ulugh Beg's flair for mathematics and astronomy was not matched by his leadership skills. When Shahrukh died in 1447, Ulugh Beg assumed the imperial throne, but he did not command enough authority to keep it. In 1449, he was beheaded by his own son. Key work: 1437 Zij Sultani. See also, Shifting Stars, Consolidating Knowledge, Mapping the Galaxies, the Copernican Model, the Tychonic Model. In context. Key astronomer: Nicholas Copernicus. Before c. 350 BCE, Aristotle places Earth at the center of the universe. c. 270 BCE, Aristarchus proposes a sun-centered universe, with the stars a vast distance away. c. 150 CE, Ptolemy publishes the Almagest. After 1576, English astronomer Thomas Digges suggests modifying the Copernican system, removing its outer edge and replacing it with a star-filled unbound space. 1605, Johannes Kepler discovers that orbits are elliptical. 1610, Galileo Galilei discovers the phases of Venus and Jupiter's moons, strengthening the heliocentric viewpoint. To most people in mid-15th century Europe, questions about Earth's place in the cosmos had been answered in the 2nd century by the Greco-Egyptian mathematician Ptolemy, who had modified ideas first put forward by Aristotle. These ideas placed Earth at the center of the cosmos, and they carried an official stamp of approval from the Church. Yet the first convincing challenge to this orthodoxy was to come from a figure within the Church, the Polish canon Nicholas Copernicus. A stationary Earth. According to the version of the universe described by Aristotle and Ptolemy, Earth was a stationary point at the center of the universe, with everything else circling around it, and stars were fixed in a large, invisible, distant sphere, which rotated rapidly around Earth. The Sun, Moon, and planets also revolved at different speeds around Earth. This idea of the universe seemed like common sense. After all, one only had to stand outside and look up at the sky, and it appeared obvious that Earth stayed in one place, while everything else rose in the east, swung across the sky, and set in the west. Furthermore, the Bible seemed to state that the Sun moves, whereas Earth does not, so anyone who contradicted this view risked being accused of heresy. Of all discoveries and opinions, none may have exerted a greater effect on the human spirit than the doctrine of Copernicus. Johann von Goethe. Nagging doubts. The Earth-centered, or geocentric, model of the universe had never convinced everyone. In fact, doubts about it had surfaced from time to time for more than 1,800 years. The most serious concern related to predicting the movements and appearances of the planets. According to the Aristotelian version of geocentrism, the planets, like all other celestial bodies, were embedded in invisible concentric spheres that revolved around Earth, each rotating at its own steady speed. But if this were true, each planet should move across the sky at a constant pace and with an unvarying brightness, and this wasn't what was observed. In so many and such important ways, then, do the planets bear witness to the Earth's mobility. Nicholas Copernicus. Ptolemy's fixes. The most glaring anomaly was Mars, which had been carefully observed in ancient times by both the Babylonians and the Chinese. It appeared to speed up and slow down from time to time. If its movements were compared to those of the rapidly rotating outer sphere of fixed stars, Mars usually moved in a particular direction, but occasionally it reversed direction, a strange behavior described as retrograde motion. In addition, its brightness varied greatly over the course of a year. Similar, but less dramatic, irregularities were also observed in the other planets. To address these problems, Ptolemy modified the original Aristotelian geocentric model. In his revised model, the planets were attached not to the concentric spheres themselves, but to circles attached to the concentric spheres. He called these circles epicycles. These were suborbits around which the planets circled, while the central pivot points of these suborbits were carried around the Sun. These modifications, Ptolemy thought, sufficed to explain the anomalies observed and matched observational data. However, his model became hugely complicated, as further epicycles needed to be added to keep prediction in line with observation. Ptolemy tried to fix some of the anomalies in Aristotle's geocentric model by proposing that each planet moved in a small circle called an epicycle. Each epicycle was embedded in a sphere called a deferent. Each planet's deferent rotated around a point slightly displaced from Earth's position in space. This point, in turn, continuously rotated around another point called an equant. Each planet had its own equant. Alternative views. From about the 4th century BCE, a number of astronomers had suggested theories refuting the geocentric model. One of these ideas was that Earth spins on its own axis, which would account for a large proportion of the daily movements of celestial objects. The concept of a rotating Earth had initially been put forward by a Greek, Heraclides Ponticus, in about 350 BCE and later by various Arabic and Indian astronomers. Supporters of geocentrism rejected his idea as absurd, believing a spinning Earth would create huge winds, such that objects on Earth's surface would simply fly off. Another idea, first proposed by Aristarchus of Samos in about 250 BCE, was that Earth might move around the Sun. Not only did this go against deeply ingrained Aristotelian ideas, but supporters of geocentrism had also for centuries cited what seemed a scientifically valid reason for ruling it out: the lack of stellar parallax. They argued that if Earth moved around the Sun, it would be possible to observe some variation in the relative positions of stars. No such variation could ever be detected, so, they said, Earth could not move. In the face of such an established philosophical tradition with little observational evidence to contradict it, and the theological arguments in favor of it, the geocentric view of the universe went unchallenged for centuries. However, in about 1545, rumors began circulating in Europe of a highly convincing challenge that had appeared in the form of a book entitled De Revolutionibus Orbium Coelestium, by a Polish scholar, Nicholas Copernicus. Copernican Revolution. The work was extremely comprehensive and proposed a new, detailed, mathematical, and geometrical model of how the universe works, based on years of astronomical observations. Copernicus's theory was based on a number of basic propositions. First, Earth rotates on its axis daily, and this rotation accounts for most of the daily movements of the stars, Sun, and planets across the sky. Copernicus thought it was just too unlikely that thousands of stars were spinning rapidly around Earth every 24 hours. Instead, he considered them to be fixed and immovable in their distant, outer sphere, and that their apparent movement was actually an illusion caused by Earth's spin. To refute the idea that a spinning Earth would create huge winds, and that objects on its surface would fly off, Copernicus pointed out that Earth's oceans and atmosphere were part of the planet and were naturally part of this spinning motion. In his own words, we would only say that not merely the Earth and the watery element joined with it have this motion, but also no small part of the air and whatever is linked in the same way to the Earth. Second, Copernicus proposed that it is the Sun that is at the center of the universe, not Earth, which is simply one of the planets, all of which circle the Sun at differing speeds. In his 1660 star atlas, German mapmaker Andreas Cellarius illustrated the cosmic systems of Ptolemy, Tycho Brahe, and Copernicus. All three still had their champions. Elegant solution. These two central tenets of Copernicus's theory were of utmost importance because they explained the movements and variation in brightness of the planets without recourse to Ptolemy's complicated adjustments. If Earth and another planet, such as Mars, both circle the Sun and do so at different speeds, taking a different amount of time to complete each revolution, they will sometimes be close to each other on the same side as the Sun and sometimes far from each other, on opposite sides to the Sun. This, at a stroke, explained the observed variations in brightness of Mars and the other planets. The heliocentric system also elegantly explained apparent retrograde motion. In place of Ptolemy's complicated epicycles, Copernicus explained that such motion could be attributed to changes in perspective caused by Earth and the other planets moving at different speeds. In the Ptolemaic model, Earth is at the center and other celestial bodies go around Earth. In the Copernican system, Earth together with the Moon have swapped position with the Sun. The sphere of the fixed stars is much farther out. Distant stars. Another of Copernicus's tenets was that the stars are much farther away from Earth and the Sun than had previously been believed. He said, "The distance between Earth and the Sun is an insignificant fraction of the distance from Earth and Sun to the stars." Earlier astronomers knew that the stars were distant, but few suspected just how far away they were, and those who did, such as Aristarchus, had not managed to convince anyone. Even Copernicus probably never realized quite how far away the stars are. It is now known that the very closest are about 260,000 times more distant than the Sun. But his assertion was extremely important because of its implications for stellar parallax. For centuries, supporters of geocentrism had argued that the absence of parallax could only be due to Earth not moving. Now, there was an alternative explanation: the parallax was not absent. But because of the great distance to the stars, it was simply too tiny to be measured with the instruments of the time. Copernicus additionally proposed that Earth is at the center of the lunar sphere. Copernicus maintained that the Moon circled Earth, as it did in the geocentric model. In his heliocentric model, the Moon moved with Earth as it circled the Sun. In this system, the Moon was the only celestial object that did not primarily move around the Sun. Though Copernicus's work was widely circulated, it took a century or more before its basic ideas were accepted by most other astronomers, let alone the public at large. One difficulty was that, although it resolved many of the problems of the Ptolemaic system, his model also contained faults that had to be amended by later astronomers. Many of these faults were due to the fact that, for philosophical reasons, Copernicus clung to the belief that all the movements of celestial bodies occurred with the objects embedded in invisible spheres and that these movements must be perfect circles. This therefore forced Copernicus to retain some of Ptolemy's epicycles in his model. The work of Johannes Kepler later replaced the idea of circular orbits with that of elliptical orbits, eliminating most of the remaining faults in Copernicus's model. It wasn't until the 1580s and the work of Danish astronomer Tycho Brahe that the idea of celestial spheres was abandoned in favor of free orbits. Those things which I am saying now may be obscure, yet they will be made clearer in their proper place. Nicholas Copernicus. In the Ptolemaic model, the occasional retrograde motion of Mars was regarded as due to loops that the planet makes in space. In the Copernican model, retrograde motion was caused simply by changes in perspective because Earth and Mars orbit the Sun at different speeds. Earth would from time to time overtake Mars on the inside as shown here, causing Mars to reverse its apparent direction of movement for several weeks. Banned by the Church. De Revolutionibus initially met with little or no resistance from the Roman Catholic Church, although some Protestants denounced it as heretical. In 1616, however, the Catholic Church condemned Copernicus's book and it remained proscribed reading for more than 200 years. The Church's decision coincided with a dispute it was having at the time with the astronomer Galileo Galilei. Galileo was an avid champion of the Copernican theory and had made discoveries in 1610 that strongly supported the heliocentric view. The dispute with Galileo caused the Church authorities to examine De Revolutionibus with intense scrutiny, and the fact that some of its propositions went against biblical texts probably led to the ban. Viewed somewhat ambivalently at first by astronomers, and prohibited by the Catholic Church, Copernicus's heliocentric model therefore took considerable time to catch on. Several centuries passed before some of its basic propositions were demonstrated to be true beyond dispute. That Earth moves in relation to the stars was eventually proved conclusively by English astronomer James Bradley in 1729. Proof that Earth spins came with the first demonstration of Foucault's pendulum in 1851. Copernicus's theory was a serious blow to old ideas about how the world and wider universe work, many of them dating from the time of Aristotle. As such, it is often cited as ushering in the scientific revolution, a series of sweeping advances in many areas of science that occurred between the 16th and 18th centuries. I am deterred by the fate of our teacher Copernicus who, although he had won immortal fame with a few, was ridiculed and condemned by countless people. Galileo Galilei. Mars's apparent retrograde motion occurs about every 26 months and lasts for 72 days. Its orbit is on a slightly different plane from Earth's, contributing to the apparent loop. Nicholas Copernicus. Nicholas Copernicus was born in Torun, Poland, in 1473. From 1491 to 1495, he studied mathematics, astronomy, and philosophy at the University of Krakow, then from 1496, canon law and astronomy at the University of Bologna, Italy. In 1497, he was appointed canon of the Cathedral of Frombork, Poland, a post he retained for life. From 1501 to 1505, he studied law, Greek, and medicine at the University of Padua, Italy. Subsequently, he returned to Frombork, where he spent much of the rest of his life. By 1508, he had begun developing his sun-centered model of the universe. He did not complete this work until 1530, although he did publish a summary of his ideas in 1514. Realizing that he risked being ridiculed or persecuted, Copernicus delayed publishing the full version of his theory until the last weeks of his life. Key works: 1514 Commentarialus, 1543 De Revolutionibus Orbium Coelestium. See also, the geocentric model, early heliocentric model, consolidating knowledge. The Tychonic model, elliptical orbits, Galileo's telescope, stellar aberration, Albatani. Introduction. The Dane Tycho Brahe was the last great astronomer of the pre-telescope era. Realizing the importance of trying to record more accurate positions, Tycho built some high-precision instruments for measuring angles. He accumulated an abundance of observations, far superior to those available to Copernicus. Magnifying the image. The realm of heavenly bodies still seemed remote and inaccessible to astronomers at the time of Tycho's death in 1601. However, the invention of the telescope around 1608 suddenly brought the distant universe into much closer proximity. Telescopes have two important advantages over eyes on their own: they have greater light-gathering power, and they can resolve finer detail. The bigger the main lens or mirror, the better the telescope on both counts. Starting in 1610, when Galileo made his first telescopic observations of the planets, the moon's rugged surface, and the star clouds of the Milky Way, the telescope became the primary tool of astronomy, opening up unimagined vistas. Planetary dynamics. After Tycho Brahe died, the records of his observations passed to his assistant Johannes Kepler, who was convinced by Copernicus's arguments that the planets orbit the sun. Armed with Tycho's data, Kepler applied his mathematical ability and intuition to discover that planetary orbits are elliptical, not circular. By 1619, he had formulated his 3 laws of planetary motion describing the geometry of how planets move. Kepler had solved the problem of how planets move, but there remained the problem of why they move as they do. The ancient Greeks had imagined that the planets were carried on invisible spheres, but Tycho had demonstrated that comets travel unhindered through interplanetary space, seeming to contradict this idea. Kepler thought that some influence from the sun impelled the planets, but he had no scientific means to describe it. If I have seen further, it is by standing on the shoulders of giants. Isaac Newton. Universal gravitation. It fell to Isaac Newton to describe the force responsible for the movement of the planets, with a theory that remained unchallenged until Einstein. Newton concluded that celestial bodies pull on each other, and he showed mathematically that Kepler's laws follow as a natural consequence if the pulling force between two bodies decreases in proportion to the square of the distance between them. Writing about this force, Newton used the word gravitas, Latin for weight, from which we get the word gravity. Improving telescopes. Newton not only created a new theoretical framework for astronomers with his mathematical way of describing how objects move, but he also applied his genius to practical matters. Early telescope makers found it impossible to obtain images free from colored distortion with their simple lenses, although it helped to make the telescope enormously long. Giovanni Domenico Cassini, for example, used long aerial telescopes without a tube to observe Saturn in the 1670s. In 1668, Newton designed and made the first working version of a reflecting telescope, which did not suffer from the color problem. Reflecting telescopes of Newton's design were widely used in the 18th century, after English inventor John Hadley developed methods for making large curved mirrors of precisely the right shape from shiny speculum metal. James Bradley, Oxford professor and later Astronomer Royal, was one astronomer who was impressed and acquired a reflector. There were also developments in lens making. In the early 18th century, English inventor Chester Moore Hulve designed a two-part lens that greatly reduced color distortion. The optician John Dolland used this invention to build much improved refracting telescopes. With high-quality telescopes now widely available, practical astronomy was transformed. In context. Key astronomer Tycho Brahe. Before 1503, the most accurate star positions to date are recorded by Bernhard Walther at Nuremberg. 1543, Copernicus introduces the idea of a sun-centered cosmos, improving the prediction of planetary positions. These, however, are still inaccurate. After 1610, Galileo's use of the telescope starts a revolution that eventually supersedes naked-eye astronomy. 1620, Johannes Kepler completes his laws of planetary motion. 1670s, major observatories are established in all the capitals of Europe. In the 16th century, the exact orbits of the planets were a mystery. Danish nobleman Tycho Brahe realized that accurate observations would need to be taken over an extended period of time if this problem were to be solved. The need for better data was underlined by the fact that a conjunction of Jupiter and Saturn in 1562, when Tycho was 17, occurred days away from the time predicted by the best available astronomical tables. Tycho undertook to take measurements along the entirety of the planet's visible paths. The astronomy of Tycho's time still followed the teachings that Aristotle had laid down nearly 1,900 years earlier. Aristotle had stated that the stars in the heavenly firmament were fixed, permanent, and unchanging. In 1572, when Tycho was 26, a bright new star was seen in the sky. It was in the constellation of Cassiopeia and stayed visible for 18 months before fading from view. Influenced by the prevailing Aristotelian dogma, most observers assumed that this was an object high in the atmosphere, but below the moon. Tycho's careful measurements of the new object convinced him that it did not move in relation to nearby stars, so he concluded that it was not an atmospheric phenomenon but a real star. The star was later discovered to be a supernova, and the remnant of this stellar explosion is still visible in the sky as Cassiopeia b. The observation of a new star was an extremely rare event. Only 8 naked-eye observations of supernovae have ever been recorded. This sighting showed that the star catalogues in use at the time did not tell the whole story. Greater precision was needed, and Tycho led the way. Precision instruments. To accomplish his task, Tycho set about constructing a collection of reliable instruments that could measure the position of a planet in the sky to an accuracy of about 0.5 arc-minute. He personally measured planetary positions over a period of around 20 years, and for this purpose in 1576 he oversaw the building of a large complex on the small island of Hven in the Øresund Strait, between what is now Denmark and Sweden. This was one of the first research institutes of its kind. Tycho carefully measured the positions of the stars and recorded them on brass plates on a spherical wooden globe about 5 feet 3 inches in diameter at his observatory on Hven. By 1595, his globe had around 1,000 stars recorded on it. It could spin around a polar axis, and a horizontal ring was used so that stars positioned above the horizon at any given time could be distinguished from those below the horizon. Tycho carried the globe with him on his travels, but it was destroyed in a fire in Copenhagen in 1728. Further evidence of a changing cosmos came from Tycho's observation of the Great Comet in 1577. Aristotle had claimed that comets were atmospheric phenomena, and this was still generally believed to be the case in the 16th century. Tycho compared measurements of the comet's position that he had taken on Hven with those that had been taken at the same time by Bohemian astronomer Thaddeus Hegesius in Prague. In both instances, the comet was observed in roughly the same place, but the moon was not, suggesting that the comet was much farther away. Tycho's observations of the way the comet moved across the sky over the months also convinced him that it was traveling through the solar system. This overturned another theory that had been believed for the previous 1,500 years. The great Greco-Egyptian astronomer Ptolemy had been convinced that the planets were embedded in real, solid, ethereal, transparent crystalline spheres, and that the spinning of these spheres moved the planets across the sky. However, Tycho observed that the comet seemed to move unhindered, and he concluded that the spheres could not exist. He therefore proposed that the planets moved unsupported through space, a daring concept at the time. Tycho used his immense wealth to design and build fine instruments, such as this armillary sphere, which was used to model the night sky as seen from Earth. No parallax. Tycho was also very interested in Copernicus's proposition that the Sun, rather than Earth, was at the center of the cosmos. If Copernicus was right, the nearby stars should appear to swing from side to side as Earth traveled annually on its orbit around the Sun, a phenomenon known as parallax. Tycho searched hard, but could not find any stellar parallax. There were two possible conclusions. The first was that the stars were too far away, meaning that the change in their position was too small for Tycho to measure with the instruments of the day. The second possibility was that Copernicus was wrong and that Earth did not move. This was Tycho's conclusion. Tycho Brahe's observatory complex on the island of Hven attracted scholars and students from all over Europe between its founding in 1576 and its closure in 1597. The Tychonic model. In reaching this conclusion, Tycho trusted his own direct experience. He did not feel Earth moving. In fact, nothing that he observed convinced him that the planet was moving. Earth appeared to be stationary and the external universe was the only thing that appeared to be in motion. This led Tycho to discard the Copernican cosmos and introduce his own. In his model of the cosmos, all the planets except Earth orbited the Sun, but the Sun and the Moon orbited a stationary Earth. For many decades after his death in 1601, Tycho's model was popular among astronomers who were dissatisfied with Ptolemy's Earth-centric system but who did not wish to anger the Catholic Church by adopting the proscribed Copernican model. However, Tycho's own insistence on observational accuracy provided the data that would lead to his idea being discredited shortly after his death. His accurate observations helped Johannes Kepler to demonstrate that the planets' orbits are ellipses and to create a model that would displace both the Tychonic and Copernican models. Tycho's improved measurements would also allow English astronomer Edmund Halley to discover the proper motion of stars in 1718. Halley realized that the bright stars Sirius, Arcturus, and Aldebaran had, by Tycho's time, moved over half a degree away from the positions recorded by Hipparchus 1,850 years earlier. Not only were the stars not fixed in the sky, but the changing positions of the closer stars could also be measured. Stellar parallax was not detected until 1838. The Tychonic model kept Earth at the center of the cosmos as in the Ptolemaic model, but the 5 known planets were now orbiting the Sun. Although he was impressed by the Copernican model, Tycho believed that Earth did not move. Tycho Brahe. Born a nobleman in 1546 in Scania, Tyche Ottesen Brahe became an astronomer after sighting a predicted solar eclipse in 1560. In 1575, King Frederick II gave Tycho the island of Hven in the Øresund Strait, where he built an observatory. Tycho later fell out with Frederick's successor, Christian IV, over the potential transfer of the island to his children and closed the observatory. In 1599, he was appointed imperial mathematician to Emperor Rudolf II in Prague. There, Tycho appointed Johannes Kepler as his assistant. Tycho was famed for his distinctive metal nose, the legacy of a duel he fought as a student. He died in 1601, allegedly of a burst bladder, having refused out of politeness to take a toilet break during a long royal banquet. Key work: 1588 Astronomii Instaurati Progymnasmata. See also, the geocentric model consolidating knowledge, the Copernican model elliptical orbits Hevelius. In context. Key astronomer David Fabricius. Before 350 BCE Greek philosopher Aristotle asserts that the stars are fixed and unchanging. After 1667 Italian astronomer Geminiano Montanari notes that the star Algol varies in brightness. 1784 John Goodricke discovers Delta Cephei, a star that varies in brightness over 5 days. English astronomer Edward Pigott discovers the variable Eta Aquili. 19th century different kinds of variable star are discovered, including long-period variables, cataclysmic variables, novae, and supernovae stars. 1912 Henrietta Swan Leavitt discovers a relationship between the periods and the brightness of variable stars such as Delta Cephei. Before the work of German astronomer David Fabricius, it was thought that there were only 2 types of star. The first were those of constant brightness, such as the 2,500 or so that can be seen with the naked eye above the horizon on a clear dark night. The second type were the new stars, such as those seen by Tycho Brahe in 1572 and Johannes Kepler in 1604. The constant stars were synonymous with the fixed, permanent stars in the ancient Greek cosmos, those that mapped out the patterns in the constellations and never changed. The new stars, by contrast, would appear unexpectedly, apparently from nowhere, then fade away, never to be seen again. A third kind of star. While observing the star Mira Ceti, in the constellation of Cetus the Whale, Fabricius realized that there was a third type of star in the sky, one that regularly varied in brightness. He made his discovery in August 1596 as he was plotting the movement of Jupiter across the sky in relation to a nearby star. To Fabricius's amazement, a few days later, the brightness of this star had increased by a factor of about 3. After a few weeks, it disappeared from view altogether, only to reappear some years later. In 1609, Fabricius confirmed that Mira Ceti was a periodic variable star, showing that, contrary to the prevailing Greek philosophy that the cosmos was unchanging, stars were not constant. Working with his son Johannes, Fabricius also used a camera obscura to look at the sun. They studied sunspots, observing that the spots moved across the sun's disk from east to west at a constant speed. They then disappeared, only to reappear on the other side, having been out of sight for the same time that it had taken them to move across the sun's disk. This was the first concrete evidence that the sun rotated, providing further proof of the variable nature of heavenly bodies. However, the book they published on the subject in 1611 was mostly overlooked, and the credit for describing the movement of sunspots went to Galileo, who published his results in 1613. An artist's impression shows material flowing from Mira A onto the hot disk around its companion white dwarf Mira B. The hot gas in the system emits X-rays. Double star system. It is now known that Mira Ceti is a double star system 420 light-years away. Mira A is an unstable red giant star, about 6 billion years old and in a late phase of its evolution. It pulses in and out, changing not only its size but also its temperature. During the cooler part of its cycle, it emits much of its energy as infrared radiation rather than light, so its brightness diminishes dramatically. Mira B is a white dwarf star surrounded by a disk of hot gas that is flowing from Mira A. In short, this new star signifies peace, as well as change in the empire for the better. David Fabricius in a letter to Johannes Kepler. David Fabricius. David Fabricius was born in 1564 in Esens, Germany, and studied at the University of Helmstedt. He later became a Lutheran pastor for a group of churches in Frisia. Together with his son Johannes, he was fascinated by astronomy and an avid user of early telescopes, which his son had brought back with him from a trip to the Netherlands. Fabricius corresponded extensively with Johannes Kepler, with whom Fabricius pioneered the use of a camera obscura to observe the sun. Little is known of Fabricius's life beyond his letters and publications. He died in 1617 after he was struck on the head with a shovel by a local goose thief, whom he had denounced from the pulpit. Key work. 1611 Narration on spots observed on the Sun and their apparent rotation with the Sun. See also, the geocentric model. The Tychonic model. Elliptical orbits. Variable stars measuring the universe. In context. Key astronomer. Johannes Kepler. Before 530–400 BCE, the works of Plato and Pythagoras convince Kepler that the cosmos can be explained using mathematics. 1543 Copernicus's sun-centered cosmos helps astronomers to visualize a physical solar system but still gives no indication as to the true shape of a planetary orbit. 1600 Tycho Brahe convinces Kepler of the reliability of his planetary observations. After 1687 Isaac Newton realizes that an inverse square law of gravitational force explains why the planets obey Kepler's laws. 1716 Edmund Halley uses observations of the transit of Venus to convert Kepler's ratios of planetary distance from the Sun into absolute values. Before the 17th century, all astronomers were also astrologers. For many, including German astronomer Johannes Kepler, casting horoscopes was the main source of their income and influence. Knowing where the planets had been in the sky was important, but of greater significance for constructing astrological charts was the ability to predict where the planets would be over the next few decades. To make predictions, astrologers assumed that the planets moved on specific paths around a central object. Before Copernicus, in the 16th century, this central body was thought by most to be Earth. Copernicus showed how the mathematics of planetary prediction could be simplified by assuming that the central body was the Sun. However, Copernicus assumed that orbits were circular, and to provide any reasonable predictive accuracy, his system still required the planets to move around a small circle, the center of which moved around a larger circle. These circular velocities were always assumed to be constant. Kepler supported the Copernican system, but the planetary tables it produced could still easily be out by a day or two. The planets, the Sun, and the Moon always appeared in a certain band of the sky, known as the ecliptic, but actual paths of individual planets around the Sun were still a mystery, as was the mechanism that made them move. Kepler was never satisfied by a moderate agreement between theory and observation. The theory had to fit exactly, otherwise some new possibility had to be tried. Fred Hoyle. Kepler's most productive years came in Prague under the patronage of Holy Roman Emperor Rudolf II. Rudolf was particularly interested in astrology and alchemy. Finding the paths. To improve the predictive tables, Danish astronomer Tycho Brahe spent more than 20 years observing the planets. He next tried to ascertain a path of each planet through space that would fit the observational data. This is where the mathematical abilities of Kepler, Brahe's assistant, came into play. He considered specific models for the solar system and the paths of the individual planets in turn, including circular and ovoid orbits. After many calculations, Kepler determined whether or not the model led to predictions of planetary positions that fit into Tycho's precise observations. If there was not exact agreement, he would discard the idea and start the process again. Abandoning circles. In 1608, after 10 years of work, Kepler found the solution, which involved abandoning both circles and constant velocity. The planets made an ellipse, a kind of stretched-out circle for which the amount of stretching is measured by a quantity called an eccentricity. Ellipses have two foci. The distance of a point on an ellipse from one focus plus the distance from the other focus is always constant. Kepler found that the Sun was at one of these two foci. These two facts made up his first law of planetary motion. The motion of the planets is an ellipse with the Sun as one of the two foci. Kepler also noticed that the speed of a planet on its ellipse was always changing, and that this change followed a fixed law: a line between the planet and the Sun sweeps out equal areas in equal times. These two laws were published in his 1609 book Astronomia Nova. Kepler had chosen to investigate Mars, which had strong astrological significance, thought to influence human desire and action. Mars took variable retrograde loops, periods during which it would reverse its direction of movement, and large variations in brightness. It also had an orbital period of only 1.88 Earth years, meaning that Mars went around the Sun about 11 times in Tycho's dataset. Kepler was lucky to have chosen Mars, since its orbit has a high eccentricity, or stretch, 0.093. This is 14 times the eccentricity of Venus. It took him another 12 years to show that the other planets also had elliptical orbits. Studying Brahe's observations, Kepler was also able to work out the planets' orbital periods. Earth goes around the Sun in 1 year, Mars in 1.88 Earth years, Jupiter in 11.86. and Saturn in 29.45. Kepler realized that the square of the orbital period was proportional to the cube of the planet's average distance from the Sun. This became his third law, and he published it in 1619 in his book Harmonics Mundi, alongside lengthy tracts on astrology, planetary music, and Platonic figures. The book had taken him 20 years to produce. When just one body goes around a larger body undisturbed, the paths it can follow are known as Kepler orbits. These are a group of curves called conic sections, which include ellipses, parabolas, and hyperbolas. The shape of the orbit is defined by a property called eccentricity. An eccentricity of 0 is a circle. Eccentricity between 0 and 1 is an ellipse. Eccentricity equal to 1 produces a parabola, and greater than 1 a hyperbola. Searching for meaning. Kepler was fascinated by patterns he found in the orbits of the planets. He noted that, once you accepted the Copernican system for the cosmos, the size of the orbits of the 6 planets, Mercury, Venus, Earth, Mars, Jupiter, and Saturn, appeared in the ratios 8:15, 20:30, 115, 195. Today, astronomers might look at a list of planetary orbital sizes and eccentricities and regard them as the result of the planetary formation process coupled with a few billion years of change. To Kepler, however, the numbers needed explanation. A deeply religious man, Kepler searched for a divine purpose within his scientific work. Since he saw 6 planets, he presumed that the number 6 must have a profound significance. He produced an ordered geometric model of the solar system in which the sun-centered spheres that contained each planetary orbit were inscribed and circumscribed by a specific regular, Platonic, solid. The sphere containing the orbit of Mercury was placed inside an octahedron. The sphere that just touched the points of this regular solid contained the orbit of Venus. This in its turn was placed inside an icosahedron. Then followed the orbit of Earth, a dodecahedron, Mars, a tetrahedron, Jupiter, a cube, and finally Saturn. The system was beautifully ordered, but inaccurate. Kepler's great breakthrough was his calculation of the actual form of the planetary orbits, but the physics behind his 3 laws did not seem to concern him. Rather, he suggested that Mars was carried on its orbit by an angel in a chariot, or swept along by some magnetic influence emanating from the Sun. The idea that the movements were due to a gravitational force only arrived with the ideas of Isaac Newton some 70 years later. According to Kepler's second law, the line joining a planet to the Sun sweeps out equal areas in equal times. This is also known as the law of equal areas. It is represented by the equal areas of the 3 shaded areas ABS, CDS, and EFS. It takes as long to travel from A to B as from C to D and from E to F. A planet moves most rapidly when it is nearest the Sun, at perihelion. A planet's slowest motion occurs when it is farthest from the Sun, at aphelion. Wider contributions. Kepler also made important advances in the study of optics, and his 1604 book Astronomiae Pars Optica is regarded as the pioneer tome in the subject. Galileo's telescope interested him greatly, and he even suggested an improved design using convex lenses for both the objective and the magnifying eyepiece. He wrote, too, about the supernova that was first seen in October 1604, today commonly called Kepler's supernova. Following Tycho, Kepler realized that the heavens could change, contradicting Aristotle's idea of a fixed cosmos. A recent planetary conjunction coupled with this new star led him to speculate about the biblical Star of Bethlehem. Kepler's fervent imagination also produced the book Somnium, in which he discusses space travel to the Moon and the lunar geography a visitor might expect on arrival. Many regard this as the first work of science fiction. Kepler's most influential publication, however, was a textbook on astronomy called Epitome Astronomiae Copernicani, and this became the most widely used astronomical work between 1630 and 1650. He ensured that the Rudolphine tables were eventually published, and these tables of predicted planetary positions helped him greatly with the well-paid calendars that he published between 1617 and 1624. The accuracy of his tables, proven over a few decades, also did much to encourage the acceptance of both the Copernican sun-centered solar system and Kepler's own three laws. Kepler was convinced that God created the world in accordance with the principle of perfect numbers, so that the underlying mathematical harmony is the real and discoverable cause of the planetary motion. William Dampier, science historian. In Harmonics Mundi, Kepler experimented with regular shapes to unlock the secrets of the cosmos. He linked these shapes with harmonics to suggest at music of the spheres. Johannes Kepler. Born prematurely in 1571, Kepler spent his childhood in Leonberg, Swabia, in his grandfather's inn. Smallpox affected his coordination and vision. A scholarship enabled him to attend the Lutheran University of Tübingen in 1589, where he was taught by Michael Maestlin, Germany's top astronomer at the time. In 1600, Tycho Brahe invited Kepler to work with him at Castle Banatki near Prague. On Tycho's death in 1601, Kepler succeeded him as imperial mathematician. In 1611, Kepler's wife died, and he became a teacher in Linz. He remarried and had 7 more children, 5 of whom died young. His work was then disrupted between 1615 and 1621 while he defended his mother from charges of witchcraft. The Catholic Counter-Reformation in 1625 caused him further problems, and prevented his return to Tübingen. Kepler died of a fever in 1630. Key work 1609 Astronomia Nova 1619 Harmonics Mundi 1627 Rudolphine tables. See also, the Copernican model, the Tychonic model, Galileo's telescope, gravitational theory, Halley's comet. In context. Key astronomer Galileo Galilei. Before 1543 Nicholas Copernicus proposes a theory of a sun-centered cosmos, but proof is needed because Earth does not seem to move. 1608 Dutch eyeglass makers developed the first telescopes. After 1656 Dutch scientist Christian Huygens builds ever bigger telescopes that are capable of detecting more detail and fainter objects. 1668 Isaac Newton produces the first reflecting telescope, an instrument that is far less affected by the distortion of chromatic aberration. 1733 The first flint glass crown glass achromatic lens is made. This greatly improves the potential image quality of refracting telescopes. Galileo Galilei's effective use of a telescope marked a watershed in the history of astronomy. There have been other turning points, such as the introduction of photography, the discovery of cosmic radio waves, and the invention of the electronic computer, but the invention of the telescope was fundamental to the advancement of the subject. The Milky Way is nothing else but a mass of innumerable stars planted together in clusters. Galileo Galilei. Limits of the naked eye. Before Galileo, the naked eye was all that was available to observe the sky. The naked eye is limited in 2 main ways: it is unable to record detail, and it can only detect objects that are reasonably bright. When looking at a full moon, the lunar diameter subtends an angle of degree at Earth's surface. This means that 2 lines extending from opposite sides of the moon meet at the eye to make an angle of degree. However, the naked eye can only detect separate objects that are more than about 60 apart. This is the eye's resolution, and determines the level of detail it can detect. Looking at the full moon with the naked eye, the lunar diameter is resolved into only 30 picture elements, analogous to individual pixels in a digital photograph. Dark lunar seas and lighter lunar highland are discernible, but individual mountains and their shadows are beyond detection. Looking up at the night sky on a cloud-free, moonless night in Galileo's Italian countryside, 2,500 stars would be visible above the horizon. The Milky Way, the disk of the solar system seen side-on, looks like a river of milk to the naked eye. Only a telescope shows that the Milky Way seems to be made up of individual stars. The bigger the telescope, the more stars are visible. By turning his new telescope to the night sky, Galileo would become one of the very first people to appreciate the true nature of this band of stars across the sky. The resolution of the naked eye is about 60 degrees. The moon subtends an angle of degree seen from Earth, meaning that the lunar diameter can be resolved into 30 picture elements. Galileo demonstrates his telescope to Leonardo Donato, the Doge of Venice. Like other astronomers of his time, Galileo relied on patronage to fund and legitimize his work. Building a telescope. Galileo did not invent the telescope himself. The idea of combining two lenses, a large one at the front of a tube to collect the light, and a small one at the back to magnify the image, had come from the Dutchmen Hans Lippershey, Jacob Medius, and Zacharias Janssen in around September 1608. After hearing about this new instrument, Galileo had resolved to make one for himself. A telescope does two important things. Its resolution is proportional to the diameter of the objective lens, the large lens at the front that collects the light. The larger the objective lens, the better the resolution. An eye that has fully adapted to the dark has a pupil that is about 1/4 in across, and a resolution of around 60. Put the eye at the back of a telescope with an objective lens of 1, 2, or 4 centimeters diameter, and the resolution improves to 120, 240, and 480 respectively. Details then spring into view. Jupiter, for example, looks like a disk and not just a point. A telescope also acts as a light bucket. Every time the diameter of the objective lens is doubled, the light gathered increases by a factor of 4, and objects of similar light output can be detected if they are twice as far away. Objective lenses of 1, 2, and 4 centimeters enable the eye to discern 20,000, 160,000, and 1,280,000 stars respectively. Galileo was not satisfied with his first instrument, which only magnified 3 times. He realized that a telescope's magnification was directly related to the ratio of the focal length of the objective lens to the focal length of the eyepiece. A longer focus convex lens for the objective, or a shorter focus concave lens for the eyepiece was required. Since these were not available, Galileo taught himself to grind and polish lenses and made them for himself. Living in northern Italy, the glassmaking center of the world at the time, helped him considerably. He eventually developed a new telescope with 33 times magnification, and it was with this improved instrument that he discovered the Jovian moons. My dear Kepler, what would you say of the learned who have steadfastly refused to cast a glance through the telescope? Galileo Galilei. 3 little stars. Galileo discovered the moons of the planet Jupiter on the night of January 7, 1610. At first, he thought he was looking at distant stars, but he quickly realized that the new bodies were moving around Jupiter. At the time, Galileo was a 45-year-old professor of mathematics at the University of Padua near Venice. When he published his pioneering telescopic observations, he wrote, "Through a spyglass, Jupiter presented himself. And since I had prepared for myself a superlative instrument, I saw that 3 little stars were positioned near him, small but yet very bright. Although I believed them to be among the number of fixed stars, they nevertheless intrigued me because they appeared to be arranged exactly along a straight line and parallel to the ecliptic." Refracting telescopes suffer from a problem known as chromatic aberration. The different wavelengths of light are brought to slightly different foci, so the final image is surrounded by a halo of color. Galileo had the experience of beholding the heavens as they actually are for perhaps the first time. I. Bernard Cohen. Repeated observations. Galileo's unexpected discovery fascinated him. As he observed Jupiter night after night, it soon became clear that the new stars were not beyond Jupiter, in the distant heavens. They not only accompanied the planet as it moved along its path across the sky, but also moved around the planet. Just as the moon orbits Earth every month, Galileo realized that there were 4 moons in orbit around Jupiter, staying with it as it orbited the Sun. The more distant moons took longer to complete their orbits than the closer ones. The time to complete one orbit from the inner to the outer moon is 1.77, 3.55, 7.15, and 16.69 days, respectively. The Jovian moon system looked like a small model of the Sun's planetary system. It was proof that not everything in the cosmos orbited Earth, as had been thought in pre-Copernican days. The observation of these 4 moons was a boost to the theory of the sun-centered cosmos. Galileo quickly published his discovery in his book Sidereus Nuncius, published on March 10, 1610. In the hope of advancement, Galileo dedicated the book to a former pupil of his who later became the Grand Duke of Tuscany, Cosimo II de' Medici. He named the moons the Medicean stars in honor of the 4 royal Medici brothers. This political thoughtfulness won him the position of chief mathematician and philosopher to the Medici at the University of Pisa. However, the name did not catch on. At first, many were skeptical, suggesting that the moons were no more than defects in the telescope lens. However, other pioneering telescopic astronomers such as Thomas Harriot, Joseph Gaultier de la Vadelle, and Nicolas Claude Fabry de Peiresc confirmed their existence when Jupiter returned to the night sky later in 1610, after passing behind the Sun. Galileo's telescope had a concave lens as an eyepiece. When viewing a celestial object a great distance away, the distance between the 2 lenses would equal the focal length of the objective lens minus the focal length of the eyepiece. Kepler's telescope, developed soon after, had a convex lens as an eyepiece. The length of the telescope was equal to the objective focal length plus the focal length of the eyepiece. Disputed priority. In 1614, German astronomer Simon Marius published Mundus Iovialis, in which he described Jupiter's moons and claimed to have discovered them before Galileo. Galileo would later accuse Marius of plagiarism, but it is now generally accepted that he made his discovery independently at around the same time. Marius named the moons Io, Europa, Ganymede, and Callisto after the Roman god Jupiter's love conquests, and these names are still used. They are now known collectively as the Galilean moons. Refracting telescopes. There were 2 kinds of early refracting telescope, the Galilean and the Keplerian, developed in 1611 by Johannes Kepler. They both had a long focus, large diameter lens at the front, called the objective. This collected the light and brought it to a focus. The image at the focus was magnified using the smaller, short focus eyepiece lens. The magnification of the instrument is equal to the focal length of the objective lens divided by the focal length of the eyepiece. A flatter convex objective lens reduced chromatic aberration, gave a longer focal length, and, for a fixed eyepiece, greater magnification. For this reason, telescopes became longer in the 17th century. The minimum focal length of eyepieces at the time of Galileo and Kepler was about 1.5 in. This meant that, for a magnification of x30, an objective lens with a focal length of 24.48 in was needed. Built in 1888, the huge James Lick telescope on Mount Hamilton, California, has a 36 inches lens and a focal length of 57 feet. A Jovian clock. Galileo carefully studied the changing positions of the Jovian moons from day to day. He concluded that, like the planets, their positions could be calculated in advance. Galileo saw that, if this could be done accurately, the system would act as a universal clock and could solve the problem of measuring longitude at sea. To establish longitude requires the ability to tell the time, but in Galileo's day, there were no timepieces that would work on a boat. Because Jupiter is at least 4 times farther away from Earth than the Sun, the Jovian system looks the same from anywhere on Earth, so a Jovian clock would work from anywhere. The longitude problem was finally solved with the introduction of accurate chronometers by the English clockmaker John Harrison around 1740. This was well before the orbits of Jupiter's moons had been worked out in detail. Galileo's discovery of 4 satellites around Jupiter had another interesting consequence. When Jonathan Swift published Gulliver's Travels in 1726, he predicted, in the chapter on Laputa, that Mars would have 2 moons simply because Earth had 1 and Jupiter 4. In 1877, this prediction was fortuitously proved to be correct when Asaph Hall discovered Mars's 2 small moons, Phobos and Deimos, using a new 26 inches refracting telescope at the U.S. Naval Observatory in Washington. Starting with the closest to Jupiter, the Galilean moons are, from left to right, Io, Europa, Ganymede, and Callisto. Ganymede is larger than the planet Mercury. Support for Copernicus. In Galileo's time, there was still a heated debate between believers of the old biblical theory that Earth was stationary at the center of the cosmos and Copernicus's new idea that the Earth was in orbit around the Sun. The geocentric idea stressed the uniqueness of the planet, while the heliocentric proposal made Earth just one of a family of planets. The assumption that Earth does not occupy a privileged place in the cosmos is now known as the Copernican principle. The challenge now was to find observations to prove that one theory was correct and the other false. The discovery of moons around Jupiter was great support for a sun-centered system. It was now clear that everything did not orbit around a central Earth, but there were still unanswered questions. If the sun-centered system was correct, Earth must be moving. If Earth had to travel around the Sun every year, it had to have an orbital speed of 20 miles section. In Galileo's time, the exact distance from Earth to the Sun was not known, but it was clearly far enough that Earth would need to be moving quickly, and humans cannot apprehend this movement. Also, this orbital motion should make the stars appear to swing from side to side every year in a phenomenon called stellar parallax. This again was not observed at the time. Galileo and his contemporaries did not suspect that the typical distance between stars in the Milky Way was about 500,000 times larger than the distance between Earth and the Sun, which makes stellar parallax so small that it is difficult to measure. It was not until the mid-19th century that vastly improved instruments made it possible to detect this swing. Despite these questions, Galileo considered that his findings had proved Copernicus correct beyond reasonable doubt. His discoveries also included the phases of Venus, which are best explained if the planet is in orbit around the Sun, and the fact that the Sun is spinning, shown by the movement of sunspots. By 1619, Galileo's pugnacious defense of Copernicus had drawn him into conflict with the Church, which had declared in 1616 that heliocentrism was heretical. In 1633, he appeared before the Inquisition. His books were banned, and he spent the last 10 years of his life under house arrest. The Bible shows the way to go to heaven, not the way the heavens go. Galileo Galilei. New moons. Jupiter only had 4 known moons for 283 years. A fifth satellite, Amalthea, was discovered by the American astronomer E. Barnard in 1892, using the 36 inches refractor at the Lick Observatory in California. It was the last solar system satellite to be discovered by direct observation. Subsequently, satellites have been found by the meticulous examination of photographs. The number of known Jupiter satellites had crept up to 12 by the mid-1950s, and has now reached 67. Many smaller moons may be found in the future. Galileo Galilei. Galileo Galilei was born in Pisa, Italy on February 15, 1564. He was appointed to the chair of mathematics at the University of Pisa in 1589, moving to the University of Padua in 1590. Galileo was an astronomer, physicist, mathematician, philosopher, and engineer, who played a pivotal role in the process of intellectual advances in Europe now known as the Scientific Revolution. He was the first person to effectively turn the refractor telescope on the heavens. During 1609-10, he discovered that the planet Jupiter had 4 moons, Venus underwent phase changes, the moon was mountainous, and the sun was spinning round once in about a month. He was a prolific writer and made his findings accessible to a wide audience. Key works: 1610 The Starry Messenger, 1632 Dialogue concerning the 2 chief world systems, 1638 The Discourses and Mathematical Demonstrations relating to 2 new sciences. See also, the Copernican model, the Tychonic model, elliptical orbits. Barnard. In context. Key astronomer: Jeremiah Horrocks. Before c.150 CE Ptolemy estimates the Earth-Sun distance at 1,210 times Earth's radius, around 5 million miles. 1619 Kepler's third law gives the ratio of the sizes of planetary orbits, but the absolute values are not known. 1631 French astronomer Pierre Gassendi observes a transit of Mercury across the solar disk, the first planetary transit to be recorded in history. After 1716, Edmund Halley suggests that an accurate timing of the transit of Venus could lead to an accurate Earth-Sun distance. 2012, the most recent transit of Venus takes place. The next two will be in 2117 and 2125. In 1639, a 20-year-old English astronomer named Jeremiah Horrocks predicted a transit of Venus across the face of the Sun after finding errors in tables made by Johannes Kepler. Because the transit was only 4 weeks away, Horrocks wrote to his collaborator, William Crabtree, urging him to observe it. On December 4, 1639, Horrocks and Crabtree independently set up helioscopes that focused an image of the Sun from a telescope onto a plane. They became the first people to witness a transit of Venus. As it crossed the Sun's disk, Horrocks tried to calculate Venus's size and distance. He noted that it subtended, or spanned, an angle of 76 arcseconds at Earth, which was smaller than the value guessed by Kepler. Using the ratios of planetary distances known from Kepler's third law, Horrocks calculated that the disk of Venus subtended an angle of about 28 arcseconds as seen from the Sun. Using data from a transit of Mercury that had taken place in 1631, Horrocks calculated that Mercury subtended the same angle as Venus. He guessed that all the planets subtend the same angle at the Sun, and calculated the distance from Earth to the Sun to be 59 million miles. Horrocks's guess is now known to be wrong. Earth subtends 17.8 arcseconds at the Sun, which is 93 million miles away. Nevertheless, he was the first to have a reasonably accurate idea of the size of the solar system. The most recent transit of Venus in 2012 was captured by NASA's Solar Dynamics Observatory. See also, elliptical orbits Halley's Comet. In context. Key astronomer Giovanni Domenico Cassini. Before 1610, Galileo announces the discovery of 4 moons around Jupiter. 1655, Christian Huygens discovers Titan, a moon orbiting Saturn that is 50% larger than Earth's moon. After 1801, the first asteroid is discovered in an orbit between Mars and Jupiter. 1859, Scottish physicist James Clerk Maxwell proves that Saturn's rings cannot be solid, since they would break apart under the force of gravity. 1960s onward, Indiana. Recent decades, spacecraft have gone into orbit around Jupiter and Saturn, and Voyager 2 flew by Uranus and Neptune. Large numbers of moons have been discovered. Working at the Panzano Observatory near Bologna, Italian astronomer Giovanni Cassini was provided in 1664 with a state-of-the-art refracting telescope made by Giuseppe Campini of Rome. With it, he discovered the bands and spots on Jupiter, measured the planet's spin period and polar flattening, and made observations of the orbits of Jupiter's 4 known moons. Observing Saturn. Cassini's reputation as a brilliant observer led to an invitation to oversee the completion of the new Paris Observatory. There, he turned his telescope on Saturn, the largest moon of which, Titan, had been discovered in 1655 by Christian Huygens. Cassini discovered 2 more satellites, Iapetus in 1671 and Rhea in 1672. In 1675, he noticed a large gap in the Saturnian rings and concluded, correctly, that the rings were not solid but made up of a multitude of small orbiting bodies. In 1684, he discovered 2 fainter satellites, Tethys and Dione. With these observations, Cassini single-handedly nearly doubled the number of known satellites in the solar system. This number has since increased dramatically. Jupiter and Saturn have more than 60 known satellites each. The gas giants in the outer solar system have 2 types of moon, large ones that were formed at the same time as the planet and smaller ones captured from the asteroid belt. In the inner solar system, Mars has 2 small captured asteroidal moons, while Mercury and Venus have no moons. Earth has 1 huge moon, 81 its mass, and astronomers are still not certain how it formed. The largest gap in Saturn's rings, called the Cassini division, separates the outer A ring from the inner B ring. It is 3,000 miles wide. See also, Galileo's telescope, the origin of the moon. Huygens. In context. Key astronomer Isaac Newton. Before 1609 Johannes Kepler shows that Mars has an elliptical orbit. After 1798 Henry Cavendish measures the gravitational constant for the first time. 1846 French mathematician Urbain Le Verrier uses Newton's laws to calculate the planet Neptune's position. 1915 Albert Einstein introduces general relativity and explains the gravitational force as a function of the curvature of spacetime. 2014 The gravitational constant is measured by studying the behavior of atoms. The latest figure is given as 6.67191011 mkgs. This is about 1% less than the value Henry Cavendish calculated. Gravity is the name given to the force of attraction between any two masses. It is the force that attracts all objects to Earth, giving them weight. It draws objects downward, toward the center of Earth. If the object were on the Moon, a much smaller mass than Earth, the force would be 6 times less and its weight would be 1/6 of its weight on Earth. English physicist, astronomer, and mathematician Isaac Newton was the first person to realize that gravity is a universal force, acting on all objects, and that it explains the movement of planets. To myself I am only a child playing on the beach, while vast oceans of truth lie undiscovered before me. Isaac Newton. Describing orbits. The shapes of the orbits of the planets were already well known in Newton's time, based on the 3 laws of planetary motion introduced by Johannes Kepler. Kepler's first law stated that these orbits were ellipses, with the Sun at one focus of each ellipse. The second law described the way that planets moved along their orbits more quickly when they were close to the Sun than when they were farther away. The third law described the relation between the time taken to complete one orbit and the distance from the Sun. The time taken for one orbit, squared, was equal to the cube of the average distance between the planet and the Sun. For instance, Earth goes around the Sun in 1 year, while Jupiter is 5.2 times farther away from the Sun than Earth. 5.2 cubed equals 140, and the square root of 140 gives the correct figure for 1 Jupiter year, 11.86 Earth years. However, although Kepler had correctly discovered the shapes and speeds of planetary orbits, he did not know why the planets moved as they did. In his 1609 book Astronomia Nova, he suggested that Mars was being carried around its orbit by an angel in a chariot. A year later, he had changed his mind, suggesting that the planets were magnets and were being driven around by magnetic arms extending from the spinning Sun. Newton's insight. Before Newton, several scientists, including Englishman Robert Hooke and Italian Giovanni Alfonso Borelli, suggested that there was a force of attraction between the Sun and the individual planets. They also stated that the force decreased with distance. On December 9, 1679, Hooke wrote to Newton saying that he thought the force might decrease as the inverse square of distance. However, Hooke did not publish the idea and did not possess the mathematical skills to fully demonstrate his proposition. By contrast, Newton was able to prove rigorously that an inverse square law of attractive force would result in an elliptical planetary orbit. Newton used mathematics to demonstrate that, if the force of attraction between the Sun and the planets varied precisely as an inverse square of the distance between them, this fully explained the planetary orbits and why they follow Kepler's 3 laws. This is written mathematically as F1r. It means that doubling the distance between the objects reduces the strength of the attractive force to a quarter of the original force. The Great Comet appeared in 1680, then again in 1681. John Flamsteed proposed that it was the same comet. Newton disagreed, but changed his mind after examining Flamsteed's data. The Great Comet. Newton was a shy, reclusive man, and reluctant to publish his breakthrough. 2 things forced his hand. The first was the Great Comet of 1680, and the second was the astronomer Edmund Halley. The Great Comet of 1680 was the brightest comet of the 17th century, so bright that for a short time it was visible in the daytime. 2 comets were seen, one that was approaching the Sun in November and December 1680, and another that was moving away from the Sun between late December 1680 and March 1681. As with all comets at the time, its orbit was a mystery, and the 2 sightings were at first not widely recognized as the same object. Astronomer John Flamsteed suggested that the 2 sightings might be of the same comet, which had come from the outer edge of the solar system, swung around the Sun, and moved out again. Halley was fascinated by the mysterious form of cometary orbits, and traveled to Cambridge to discuss the problem with his friend Newton. Using his law that related force to acceleration and his insistence that the strength of the force varied as the inverse square of distance, Newton calculated the parameters of the comet's orbit as it passed through the inner solar system. This breakthrough intrigued Halley so much